Now I shall shift here to a new section, Fizeau-type interferometry, and major contributors here to this here are of course Young, but also Fizeau, Stefan, Michelson, Pease, and here is just a reminder about the double slit Young experiment. So here I have represented a screen with two holes in the screen. And then the plane wave, monochromatic at wavelength lambda, represented here in orange, falling on the screen. So it comes from a very distant light source. Now the separation between the two holes is B. And if I adopt a system of coordinates x, z, and y, perpendicular to the screen, the positions of these two holes can be represented as b divided by 2, then 0, 0, of course. Now minus b divided by 2 and 0, 0. So 0, 0, x equals 0, z equals 0, y equals 0 is there. And now, if I look in a distant screen, what happens? What is the distribution of light? But this is monochromatic light at the wavelength lambda. Well, it's very easy. I know that whenever the difference in the distance of the two beams coming from the two holes is equal to an integer number of wavelengths, there will be constructive interference. And whenever it will be an odd number of half of wavelengths, it will be the destruction. So what we should do, we should estimate this quantity. What is the difference between the module of pp1 minus module of pp2? I will do that on the blackboard. Well, because it's very instructive, So let's estimate the value of this expression. And after we'll say, okay, this should be equal to an integer number of times the wavelengths. So how to proceed? So pp1. So I could say, okay, let's estimate pp high, where high is equal to 1 or to 2. So this is equal to square root of, so P has coordinate x, y, z. So it will be x minus, so it will be, let's take the first one, b half square plus y minus 0 square plus z minus 0 square. Correct? So this is pp1. So we can say here that, well, it is equal to, this is equal to what? So I will just put z in front of the square root. I will say, okay, this is equal to z multiplied by 1 plus x minus b over 2 square plus y square divided by z square. Correct? Now I shall make use of the Taylor development of this quantity. Square root of 1 plus epsilon. So to first order, do you agree that it is 1 plus epsilon over 2 plus etc. etc. So I don't make the development of that but so here I could say, okay, this will be equal to what? To z multiplied by 1 plus x minus b over 2 square plus y square divided by 2z square. Now, pp2, module pp2, well, it will be exactly, it will be something very similar. Z 1 plus, well, here it will be x plus, yeah, b over 2 square plus y square divided by 2z square. Yes? Very simple, huh? And now if I make the difference, so pp1 module pp1 minus module pp2, so I just make the subtraction of the two. And you see there are many quantities which will go away, yeah? So first, yeah, the z, yeah, I can put it z here. Here it would be 2 over z, and here it would be z, and here 2 over z. Now, this quantity will go away. It's the same. The x square will go away. The b divided by 2 square will go away. What will remain is just the double product. Yeah? So what will remain is just what? It will be x times b over 2, well, times 2, then divided by 2z, and 1 will come from here, 1 will come from there. So in principle, I should put here 4, correct? Because I have the double product from here and the double product from there, yeah? So factor 4. So this is equal finally to x times b over z. And now this should be equal to an integer number of times the wavelengths. So let's take, well, for n equals 0, it's trivial. N equals 0, yeah, will correspond to this maximum of interference. Now for n equal 1, yeah, I will move, yeah, to the secondary maximum. So let's take n equal 1. So for n equal 1, we have x times b over z equal lambda, or x over z equal lambda over b. Yeah? Now, what does represent x over z? Yeah? Well, you see, x is a distance, yeah, between two maxima. Yeah, this is x. And divided by z, the distance, yeah, between the focal plane, yeah, and the center, yeah, of the screen. So it is an angle, yeah. It is the angular separation between two maxima. So this is angular. Well, this is the power. Well, the resolution power of my interferometer, yeah. Phi is equal to lambda over b. So phi is equal x over z, and for n equal 1, it's lambda over b. So I see that, well, this gives you a resolving power, of course, yeah? And smaller is the wavelength, yeah? Well, closer will be, yeah, the maxima, or larger is the distance between the two holes, yeah? And still closer will be the distance between two consecutive maxima. Okay, now, well, Fizeau, yeah, had a very bright idea, yeah, and this will be explained on this transparency. Yeah? So he used an 80 centimeter telescope, yeah, of Marseille. So you see, this represents the objective of your telescope. It can be a lens or it can be a mirror. It doesn't make any difference. And on top of this objective, yeah, is a screen with two holes. Well, maybe one thing I forgot to mention, yeah, from my previous demonstration here, is that I see that the y quantity has disappeared. Yeah, the y quantity. Yeah, so I have x, I have z, but there is no y. And the reason is that when I made this demonstration, if it doesn't depend on y, it means that it's true for every y value. Yeah, and the reason is that what I represented in this plane, yeah, is true for all the planes, yeah, which are perpendicular to the y direction. So what I should see, yeah, in this screen here are just interference fringes. Yeah, so are fringes, in fact. Yeah, yeah, exactly. Because it's true for any value of y. Okay, now let's go back to these graphs. Yeah, so you have two holes. Now, if I would ask you, yeah, well, I just block one hole here. Yeah, and well, typically this could be 15 centimeter in diameter. Yeah, well, I just block one hole. And if I ask you, what do you see in the focal plane if I would block the light passing through the second hole? What would you see? So I block one hole with my hand, and I look in the focal plane, yeah, of my telescope. Yeah, what would I see? Airy disk. I would say an airy disk, which angular diameter is given by what? Lambda over d, where d is what? The size of the hole. You agree? Now, if instead, yeah, I block this hole, let this one open, what would I see? I would see exactly the same. Yeah. So you see the two airy disks, yeah, will reinforce the light. Yeah. But in addition, there would be interference. So I would see, of course, yeah, interference fringes, which are perpendicular, yeah, you see, they are perpendicular to the direction between the two holes, yeah, just as in the, in the previous experiment, yeah, exactly, yeah. Okay. Now, well, Fizeau, yeah, came with the following proposition. He said, well, let's assume that we observe a double star. Yeah? So there are two sources of light which are incoherent. Yeah? They are incoherent between each other. Yeah? Would you agree that one star would give you these interference fringes? Second star would give these interference fringes. Yeah? So if the stars are very well separated, yeah, well, you see two airy disks like this, yeah, very well separated. Now let's assume that the two stars are very near to each other, very near. So near that their angular separation is 0. So, of course, you would still see this, yeah? Okay. Now, let's assume that I separate the star from a very small angular distance, such that the maxima of one comes into the minima of the second one. What would happen, yeah? Is that the fringes would disappear. Yeah, you see? And so, well, Fizeau just proposed that the fringes would disappear, yeah, for an angular shift delta, which is just phi divided by 2, because we know that phi is angular distance between two maxima interferences. Yeah, so if the angular separation is half that value, yeah, there is disappearance of the fringes. Yeah, and so well, this was the intuitive idea of Fizeau. Yeah. To look at all the stars in the sky with the hope that maybe, because a star can be assimilated, yeah, to a very large number of incoherent sources of light, so that if you would resolve it, yeah, the fringes would have a contrast equal to 0. There would be a smearing, yeah, of the fringes. Yeah? So this was this idea. So whenever the angular diameter or angular separation between several stars, yeah, exceeds, yeah, half of the value of the angular resolution of your instrument, yeah, you would see a smearing of the fringes. Yeah? Like that, you see very well the fringes. It's not resolved, and then, oops, it starts being resolved, and then the contrast, yeah, of the fringes decreases. Yeah. Now, well, a quantity, yeah, that objectively measures, yeah, the contrast of the fringes, yeah, is called the visibility. And what is the visibility? Yeah, is the following quantity. It's the maximal intensity of the fringes, so this one, minus the minimum intensity of that fringe, which is darker, divided by the sum of the two. Okay, now let's assume we are in that case where I cannot resolve a star, yeah? What is the visibility? How much? So Imax is Imax. What is I mean? So visibility varies between 0 and 1, yeah? So remember that for 1, you don't resolve the star. For 0, you fully resolve the star. Okay, and so, well, in 1873, Stéphane makes use of the 80-centimeter telescope of Marseille Observatory. And well, he sets on top a screen with, in fact, 2 slits. And we will have the tools later to show that, well, the shape of the slits is not very important. Well, as long as they are similar, the two slits are similar. And they look at all the stars with the hope of resolving them, and they cannot resolve any one. They don't see any change in the contrast of the fringes after looking at hundreds of stars. So they are very disappointed. Now the separation between the 2 slits is about 65 centimeters, which corresponds to a resolving power of 0.16 second of arc. 0.16 second of arc. So they know that all the stars have an angular diameter smaller than, well, 160 milli-arc second. Okay? Remember that Newton already estimated to 3 milli-arc second the size of the stars. So no surprise. Okay, now what happened next is that Michelson had the bright idea in Berkeley to use a 30-centimeter telescope to observe the Galilean satellites, so the 4 satellites of Jupiter. And with a size of 30 centimeters, you would find that the resolving power of your telescope is about half a second of arc. And he looked at the Galilean satellites, and he could resolve them. So he could, for some of them, see the disappearance of the fringes. And then he compared their angular diameters with those values derived using other methods, classical methods, and it was perfect, in perfect agreement, And well, it's a kind of a pity that neither Fizeau, neither Stéphane, thought about doing such an experiment also, using Galilean satellites. So it was Michelson who did that, And then Michelson wanted absolutely to resolve stars. And well, his idea, so well, this is the 80-centimeter telescope of Marseille used by Fizeau and Stéphane. So let's make 10-minute breaks, and later on we shall just continue a little bit, and I will tell you how Michelson and Pease proceeded to resolve the first stars. Before going to this laboratory experiments that we'll do in about maybe 15 minutes, I will just show you how Michelson proceeded to measure the first angular diameters. So he used the 100-inch Hooker telescope on Mount Wilson that you see here. And with Pease, they just put a beam 7 meters long on top of the telescope. And you may see, well, 4 little mirrors here, so 2 inclined at 45 degrees in that direction, 2 others inclined in the opposite direction by 45 degrees too. So now you see that the light coming from a distant star falls on this mirror, goes here, is reflected by the main mirror and focus there. Now the originality, well, you can see the 4 mirrors here too, And the originality of this construction was that the 2 external mirrors could be moved apart, so changing the baseline at will. And now, well, they knew from Eddington that Alpha Orionis, Betelgeuse, was a supergiant star, red supergiant, with a diameter, well, about 400 times that of the Sun. And in spite of its very big distance, 650 light years away from us, they looked at it with this 7 meter beam interferometer, and they could resolve it. It means that they saw the smearing of the fringes. It means contrast of the fringes going to 0, by just changing the baseline. And well, the angular distance, the angular diameter they derived was 47 milliarcsecond. 47 milliarcsecond, yeah. Of course, this is more than Newton's prediction of 3 milliarcsecond, but the reason is that this is a red supergiant, yeah. So, no surprise. So you see here the image that they saw, yeah, with the eyepiece. Now, to be able, yeah, to achieve such a measurement, yeah, they had to make sure that the difference in the distance, yeah, between the two beams, yeah, coming well along this direction and that direction from the star, yeah, down to the focal plane, yeah, differs by less than typically a few microns, yeah. So it means that the beam had to be very robust, very stable, no vibration, etc., etc. Yeah? So the requested accuracy was over several microns. Okay. Now maybe what I would just add is that Anderson, yeah, one of their collaborators, used the same experiment, yeah, to resolve many spectroscopic binaries. Well, Michelson and Pease themselves, yeah, could resolve 5 diameters of stars. Yeah, so there were 4 more stars that they've been able to resolve. After that, yeah, they tried to put a beam of 15 meters long, so that they could have reached an angular resolution of about 10 milliarcsecond. Yeah, but because of the technology available at that time, yeah, vibrations, flexures, etc., yeah, they could not succeed. They tried during a few years, yeah, but the maximum baseline was 7 meters. So because of all those difficulties, yeah, well, Fizeau-type interferometry, yeah, was abandoned, yeah, and well, I didn't mention, but those measurements were made in 1920, yeah, during the winter of 1920. So it was abandoned, and then came, well, around the years 50s, yeah, another type of interferometry known as intensity interferometry, yeah, by Brown and Twiss. And this is based on a totally different principle. It's based on measuring the coherence of the light, yeah, collected by 2 independent telescopes. Yeah, it's a totally different approach. Then also, well, Antoine Labeyrie, who is a French astronomer, yeah, used what you have heard about speckle interferometry, which is still another technique. And then it was in 1975, the same Antoine Labeyrie, with a French professor, yeah, who succeeded, yeah, in using 2 independent telescopes, so not anymore a beam, yeah, on top of a telescope, but 2 independent telescopes. I think the size was 27 centimeters, and separated by up to 144 meters, yeah, and they could resolve the Vega star in the sky, yeah. But this was in 1975. So from 1920 until 1975, yeah, nothing happened, yeah, in optical interferometry. But as you know, in radio astronomy, yeah, well, interferometry was used because well, the constraints are much less severe. The constraint I mentioned for optical light, yeah, of an accuracy between the 2 paths of lights, yeah, being the same within a few microns, yeah, can be relaxed, yeah, at the radio wavelengths, because the wavelength of radio, yeah, is much larger, yeah. So now what I will propose, yeah, is to make some experiment with you. So first experiment, yeah, you will receive, yeah, a piece of cartoon, then some aluminum, little sheet of aluminum, then a needle, yeah. And what you try to do, yeah, is to make, well, near the center, a hole, yeah. So just try to make a hole very perpendicular, yeah, to the sheet, with a size of about maybe 0.5 millimeter in a diameter, yeah. It's okay, easy. Well, I think the first holes, yeah, will be bad, yeah, but you can make different holes elsewhere. Then when you find that you have a good hole, you take this piece of cartoon, yeah? You put the hole, yeah? The small holes just around the center of the big holes. Then we will give you some glue, and you may glue the piece of aluminum. Then I will put here, yeah, 2 lights, which the angular radius here is very small, and you should be able with this single hole experiment, yeah, in the aluminum, yeah, look, yeah, through your eye, and you should see the hairy disk, yeah. Well, smaller will be the hole, bigger will be the hairy disk, yeah, but fainter it will also be, yeah. So there is a compromise. So, well, typically a hole with a diameter of 0.5 millimeter, yeah, is a good size, yeah. So you have to try several times. So I will circulate it, yeah. After, there will be the second experiment, yeah. Then you take a second sheet of aluminum, and now you try to make 2 holes separated by, if possible, yeah, 1 millimeter, and with angular size, so each hole of 0.5 millimeter. So, as I say, yeah, probably the first pairs of holes you will make, yeah, won't be good, but then you can make other ones, yeah. We have plenty of aluminum paper, yeah. And then, what you should see while looking at a distant source of light, you see the airy disk, but crossed by the interference fringes, yeah. And then later, after my lecture, yeah, what you could do is the following, yeah, is, well, I would set a source of light here, and if you go far away enough, yeah, with your interferometer, you will see the fringes. And now, if you approach, when you will closer, the contrast of the fringes should decrease. And eventually, at a certain distance, you will see the smearing of the fringes, so no fringes anymore. Now you know that if you divide lambda by the distance between your 2 holes, maybe 1 millimeter, you find what is the angular size of the source of light. Now, if you know the distance, you may derive what is the linear diameter of the source of light. So it's very nice because you can do that experiment at home and play with the variation of the distance between you and the source of light, or have several interferometers with different baselines and see the different type of fringes that you may observe, yeah. So you see on your cartoon, yeah, the idea is that you set, yeah, the 1 hole experiment above, the 2 holes experiment below, then you have the 2 into 1, yeah. And this is a very interesting one. So you see that the fringes, yeah, are perpendicular, yeah, to the distance between the 2 holes. So you see here the 2 holes are almost touching each other, yeah. So the base is 0.5 millimeter in size, separated by 0.5 millimeter. This would be perfect. Not easy to do. And now, well, what's amazing, I have a question to you. Everything what I've told until now was for monochromatic light, yeah? But this is not monochromatic light. Yeah, it's white light. Why does it work? Yeah. In fact, yeah, you agree? The spacing, yeah, between the angular diameter between 2 maxima, yeah, is lambda over d, yeah? Okay, the first extremum will be for n equals 0, yeah? So this will be a maximum of white light. Now, for n equal 1, the spacing is lambda over d. So whether you take 500,000 or 600,000, it doesn't make a big difference, yeah? Yeah. So, well, if we would have very good eye, we could see a chromatic dispersion. So we could see that blue light is less separated than red light, yeah? But our vision doesn't allow us to see that, yeah? Therefore, we see, well, fringes in white light, yeah? Yeah. So now, well, because it's midday, yeah, I think it's a good time, yeah, anyway, to break. But if you still have some time, what you can try, if you have a good interferometer, is to try to get closer to the light source and see whether you see a change in the contrast, in the visibility of the fringes. Yeah. So if you are very far away, the visibility should be 1. If you get very close, the visibility should go down to 0. Yeah. And in between, you should see changes in visibility. So it's a very nice, simple experiment, yeah, to visualize, yeah, what interferometry is about. Yeah. So next time, what we will do, well, I will address the problem of the coherence of light. Yeah, exactly the fact that astronomers don't work with white light. They don't work with monochromatic light, because if you work with monochromatic light, it means that the bandpass, yeah, is so narrow that you don't get any photons. Yeah, but they work, yeah, with a narrow band. Yeah, and then we produce what is known as quasi-monochromatic light. So it's not monochromatic, but quasi-monochromatic. And so these are the different sections that we'll see next time. Yeah, with a very important theorems. Yeah, and then some very nice results. Yeah, so it will be a little bit more theoretical. Yeah, next time.